speaker today is Dr. Matt Hollister. Matt Hollister's educational background begins with an undergraduate degree at the University of York, followed by a PhD from the University of Edinburgh, working on the SCUBA 2 bolometric instrument. To give you an idea of timescale, SCUBA 2 was the advancement to an earlier telescope named SCUBA, which was revolutionary for the time, but was only an 8-pixel camera, effectively, in its production. So this was a forefront piece of technology, where we've seen phenomenal development in recent years. After that, he took up a postdoc at Caltech, and has followed that up with becoming a star scientist in that position, and now he'll tell us about his most recent work. As he'll describe in his talk, Matt works about 1.5 miles underground, so I refer to him affectionately as the Morlock. So with that said, let us welcome the Morlock himself, Matt Hollister.
Okay, thank you very much for that introduction, Tom. I'll have words with you about that later on. So yes, as very kindly introduced there, my name is Matt Hollister. I'm currently a staff physicist at the Fermi National Accelerator Laboratory near Chicago, Illinois. I've been in that position for about 2 years, mostly working on ultra-sensitive dark matter experiments. I apologize for my talk title, a little bit of word salad there, but hopefully I'll lay out a reasonable case for what we're doing and some of the more interesting aspects of how we do this kind of experiment as we go. So very briefly, since this is a What Physicists Do series, I'll just give a very quick outline of my career. It's been a little bit unconventional compared to some physicists working in the field. Then actually get on to some actual technical meat. So a little bit of the history of dark matter. Goes back further than people might think. Hopefully I can convince you that this stuff does actually exist and that we're not on a complete wild goose chase to try to find it. Then I'll talk a little bit about one particular experiment, which is part of the scientific collaboration that I'm currently involved in, a series of experiments called CDMS, the Cryogenic Dark Matter Search. In particular, focusing the latest generation of this experiment, which we're currently constructing with a goal to deploy this guy 1.5 miles underground in Canada, starting over the next couple of years. And then very briefly at the end, I'll just try to give you a flavour of what it's like to work in this very, very unusual laboratory environment. So, as Tom mentioned, I am a physicist, although I've never really worked in research. I've always been more interested and more focused in the actual experimental construction, supporting other research programs. So I did my undergraduate master's in physics with astrophysics at the University of York in the UK, and then went on to a PhD in astronomy at the University of Edinburgh, which is where I met your own Professor Target. It was a PhD in astronomy, although the only astronomy was one pretty picture in my thesis. Really, I was an engineer, but I have this astronomy PhD just because of the vagaries of the way the university issues diplomas. Following that, I spent a number of years as a postdoc at Caltech down in Los Angeles, and also some time at NASA's Jet Propulsion Laboratory before being hired on as a staff scientist. I primarily worked in the construction of instrumentation for sub-millimeter astronomy. Later on, I branched out a little bit into building instrumentation for the NASA Airborne Science Program. So I went from being up a mountain at 14,000 feet in sunny Hawaii to being on research aircraft such as the Sphere Airborne Telescope, which we see on the left here. This is a relatively newly deployed instrument. This, as you probably can tell, is a converted 747 with a 4-meter infrared telescope just nestled in the back of the plane there. This is one of the premier mid-infrared research platforms. It's a lot cheaper to operate this thing than it is to launch a satellite, but you can still get above most of the Earth's atmosphere as you go up and cruise around at about 40,000 feet for 6 or 7 hours. In addition to this kind of work, I was also building Earth observation instruments flying from various high-altitude research planes. In this case, NASA's DR2 high-altitude research aircraft. This plane, although the instruments are looking down, this guy operates about 80,000 feet. So that's right at the edge of space. So we're covering a pretty broad range of altitude. These days, though, I spend more of my time underground. So my running joke is that the delta for my instruments is about 6,800 feet below ground to about 80,000 feet above. 2 years ago, my wife and I made a fairly major move to Illinois, where I took up a position initially in the low temperature cryogenics group at the Fermi National Accelerator Laboratory. Fermilab is one of the DOE's premier centres for high-energy particle physics. There's some accelerator work going on there. And this beautiful aerial shot of the lab. For scale, the whole lab is about 5,000 acres. Most of the laboratory is underground though, so we have beautiful prairie above it, including our bison. We're currently up to 5 babies at the moment that we left. There's probably going to be a few more by the time we get back. After several reorganisations at the lab, my current position is as lead of what has the grandiose title of the Sub-Kelvin Cryogenics Group. We mostly do deep cryogenic work supporting both the particle physics program at the lab, but also a lot of quantum computing work, which is a very exciting frontier that the DOE is breaking into in a big way recently. So enough about me. We'll move on to a little bit of history here. So as I mentioned, the history of dark matter actually is a lot longer than a lot of people realise. The first suggestion that there might be some exotic form of matter which was non-luminous actually dates back to around the early 1880s. Our very own William Thomson, First Lord Kelvin, in his brief phase dabbling in astronomy rather than thermodynamics, noticed that the stellar motion of a lot of bodies around the centre of the Milky Way was such that it didn't really match up with the classical Newtonian dynamics. This is going to be a constant theme through the development of the early years of dark matter as a field. But he suggested that there was something there which we couldn't see, but that was gravitationally influencing the bodies that we can see. He used the phrase dark bodies because in his mind what these objects were actually non-shining stars, maybe other rocky bodies just floating in free space that he wasn't able to see but that was interacting with his environment. The first mention of dark matter actually dates to around 1906 by Henri Poincaré, who was talking about William Thomson's work. He was a philosopher, he didn't really do any physics, but he did want to comment on a lot of the earlier work around him. So he's really the first one who coined this term. Then moving in later into the early part of the 1900s, there was further work being done by a number of the really pioneering optical astronomers in Europe. Jacobus Catéen in the 1920s, followed by Jan Oort in the 1930s. They used very similar observations to the data that William Thomson had first used to actually suggest that these objects in space really aren't behaving in the way that we would expect from what should have been a well-understood theory of gravity at the time. These days, it's generally accepted that Jan Oort's measurement were actually the result of experimental error. So he doesn't get much credit in this field, but it could easily have gone either way. So what are we actually talking about here when we're talking about these stellar motions? So really what it comes down to is what's broadly termed rotation curves. Now, we're able to use astronomical observations to measure how different parts of galaxies are actually moving. This is very simply done using the Doppler effect. If you look at a typical sort of edge-on rotating spiral galaxy, you can see differences in the Doppler shift of different parts of this galaxy depending on how it's moving relative to the observer. So obviously this very simplified cartoon plot on the left here, if we're looking at this edge-on spiral, what we see in the center is essentially no motion at all. The spiral arms that are moving towards us are blue shifted, the spiral arms moving away from us are red shifted. So in this very, very simple picture, this gives us a way to measure how the galaxy is rotating. But critically, we're able to measure how it's rotating as a function of the radius from the center. Now, if what we're seeing is purely luminous matter, which basically stars, planets, gas, things we could conventionally see, what we should see according to classical dynamics is that as we move to a larger radius, the rotation velocity reduces. So that would be curve A in the simplified plot here on the right. But what we actually measure is something that looks more like curve B. So we have an initial rise as we come away from point B in the center, but then instead of an R squared drop off as we would expect to see as the amount of mass in the rotational structure reduces, we actually see this flattening. Now, one way to interpret this unusual velocity profile is that there's actually more mass out here than we're able to see. That's really the origin of what the early pioneers, such as William Thomson, were seeing in their pioneering observations of these galaxies. So now this brings us up to the early 1930s, and one of my favourite historical astronomy figures, Fritz Zwicky here. He was a Swiss astronomer that was working in the US, primarily at Caltech. And early in his career, he was able to do some very, very detailed rotation curve measurements for much larger structures than simply galaxies. He was looking at the Coma cluster, of which we have a really nice, more recent wide field image of the Coma cluster here, just next to our friend Zwicky. And again, by looking at these rotational dynamics, he inferred that there was approximately 400 times as much mass in this cluster as was actually visible. That was the only way that he could explain the orbital dynamics that he was seeing. Interestingly, his estimate was off by about an order of magnitude, but that's because he was using an inaccurate version of Hubble's constant. If we go back and reanalyze his data now with a more refined number for that constant, you actually get a figure for the dark matter fraction which is much more realistic. And around the same time, another slightly unsung figure is Horace Babcock. In 1939, he published a very detailed study of the rotation of the Andromeda Galaxy M31, which is our closest galactic neighbor. And he saw this very, very familiar flattening of the rotation curve as well. So while he published this very detailed study of the rotation, he actually didn't attribute this to the presence of some sort of non-luminous matter. So at the time this idea was very, very new, it really wasn't accepted. Most people were trying to find ways to explain what people were seeing without having to invoke magic, essentially, for want of a better term, that there was something there we weren't able to see. Moving on now to the early 1970s, this is where things really started to hot up. This was the work of a very famous astronomer, Vera Rubin, who I believe actually was one of the first speakers here on this very seminar series, looking back on the history of this particular program. While working at the Palomar Observatory using a very, very sensitive spectrometer built by this gentleman here, Ken Ford, she was able to get a very good, very detailed rotation curve, not only for Andromeda, but for a number of other edge-on spiral galaxies. So this was one of the first sets of evidence that this same effect wasn't something that was just an isolated phenomenon. You could essentially pick any galaxy that you wanted and measure this same sort of behavior. Further data from the program work from Rubin, Ford, and a number of collaborators published in the early 1980s refined these estimates for the dark matter fraction in these galaxies to around 5 to 6 times as much mass as was actually visible from conventional photometry. And around the same time, radio astronomy was really starting to take off. Prior to the Second World War, radio astronomy simply wasn't a thing. But with the advent of a lot of technology for radar and other communication systems, people were really able to start measuring these radio signals coming from deep space. So, of course, one of the first things they did was start measuring galaxy rotation curves, because this is exactly the sort of thing that a radio observation is set up for. It's the Doppler effect is exactly what you would expect to see in radio direction finding, for example. So a number of groups working essentially simultaneously both at the Jodrell Bank Observatory in the UK and at Green Bank in West Virginia. This is not a picture of the current Green Bank telescope, of course, because this one fell down in the 1960s and had to be replaced with a more modern telescope, which is there now. But a number of these results from these independent studies started to increase the available data for rotation curves, this time pushing into the radio wavelengths, which is extremely important because the radio signals can be measured in galaxies out to a much larger radius than the visible sort of conventional luminous photometry. But again, they found exactly the same things, but the fact that they were able to do it to these much larger radii, in the case of the Andromeda Galaxy, up to about twice the radii from the center that Rubin and Ford were able to measure, this sort of further added weight to the evidence that this was a real effect and it wasn't the result of something like instrumentation error. Later in the early 1970s, a group led by Rogstad and Shostak were actually able to measure a number of very distant galaxies, this time using the Owens Valley interferometry here in Central California. They published results for around 5 very distant galaxies, again confirming exactly the same effect that these other groups have been seeing. So to put this into some degree of context, this is a modern quasic rotation curve. But it does show the same sort of effect very, very nicely. So this is, for M33, which is another nearby spiral galaxy. We can see here at the inner radii, we can plot the rotation curve based on visible light and near-infrared data. And then out at the larger radii using the 21 centimeter hydrogen line from radio telescopes. And this not only shows the flat profile, but it actually shows an increasing rotational velocity. So whereas we would, in previous examples, have seen this flattening, there's a higher concentration, or what believed to be a higher concentration of dark matter in this galaxy, which is actually causing the outer parts of the galaxy essentially to be accelerated versus the inner core. But as all good skeptical scientists, we shouldn't automatically jump to conclusions. So is it really necessary to invoke this magical dark matter particle? Of course, people still try to explain it without invoking this new form of matter. There have been a number of theories presented trying to explain the behavior that's seen in these galaxies as a result of some sort of change to classical Newtonian dynamics. One of the first theories was presented by Milgram in the early 1980s. He first coined the phrase modified Newtonian dynamics. Essentially what this suggests is that classical gravitational dynamics only really works at very small scale. As soon as you're out at these immensely large distances, out at the edges of galaxies and also in much larger structures such as the Coma cluster, there's actually very low-level modifications to the conventional theory of gravity, which can explain the flattening of the rotation curves. Unfortunately, these theories can be very good at explaining one piece of evidence, but even at the time Milgram was proposing this, there was a lot of very, very separate and independent observations, all of which could be explained by dark matter, but all of which could not be explained by a simple modification to Newtonian dynamics. So simply by applying the principle of Occam's razor, it suggests that dark matter really is the preferred theory. One of the major nails in the coffin for theories such as Mons was observations of this object here, which is called the bullet cluster. What's going on here is that we have two galaxy clusters are actually in the process of colliding. They pass through each other and out the other side. And what we see is the result of this huge amounts of mass interacting with each other as the two clusters have collided. So the image I have here on the right is a composite. We can see the conventional matter, the stars, galaxies, are all clustered around here. The pink colouring here near the centre is tracing gas clouds, so this is largely elemental hydrogen and helium. The blue colouring is the inferred presence of dark matter. And this has been measured by looking at gravitational lensing from a lot of these large objects in the background. Now, if there was no dark matter and this was simply a gravitational interaction, we would expect this gravitational lensing to actually map where we can place the conventional luminous matter. But as we can see from this image, there's actually a major separation between the lensing effects and the luminous matter. So this same effect is seen in a number of other clusters, but this in itself is really strong evidence that there is something more exotic going on here than simple modifications to the gravitational dynamic. So the current state of the art, there's some variation in the numbers I'm going to quote here, but as various measurements have been refined, these numbers have shifted around by a few fractions of a percent. But the generally accepted paradigm is that our universe is actually only a minority matter. The vast majority of the universe is formed of this exotic substance called dark energy, which I'm not going to be talking about today. That's a whole seminar subject in and of itself. The conventional matter, everything that we're made of, stars, planets, everything we can see, actually only occupies this little 5% sliver here shown in yellow. There's then about 5 times as much dark matter, and that in itself is dwarfed by the dark energy fraction. So there's a huge amount of physics buried in this sort of 30% pi segment here, and probably an automatic Nobel Prize if we can detect these things. So hopefully I've convinced you that dark matter is a real thing. Now we have to start asking the question, what actually is this stuff? So the first obvious question is, okay, could it just be something more akin to normal matter that we see around us, but that isn't luminous? This was a very serious theoretical suggestion for a while, although again it's mostly fallen out of favour as our understanding of the universe and new measurements have come to light. These sort of non-luminous baryonic materials were all lumped together into a class of particle known as MACHOs, massive astrophysical compact halo objects or something. These could be something very exotic, could be something simple as a large number of dead stellar cores, white dwarfs, brown dwarfs, primordial black holes, a whole raft of objects which could account for mass, but which we're not able to see in conventional photometry or radio observation. There's a couple of problems with this theory, though. One of which is that the current models of Big Bang nucleosynthesis actually predict the abundance of light elements that we observe. If there were a lot more baryons being produced at the Big Bang, then we would also expect to see a lot more hydrogen, helium, and lithium. And that elemental gas simply isn't there. More recent work in gravitational microlensing has also shown us that while there are a lot of candidate MACHO-type objects around, a lot of which probably are black holes, they can really only account for a very small fraction of the amount of mass that we need to explain the broader observations. And finally, very recent results from measurements of the cosmic microwave background anisotropy actually support this idea that only around 84% of the of the matter that we see is interacting gravitationally only. So again, this is consistent with this 5% baryon to 26% non-baryonic dark matter ratio that we see from our observations. So, if it's non-baryonic, what sort of non-baryon is it? Over the years, there have been a large number of possible particles proposed to explain what this dark matter actually is, some of which have now fallen out of favour. One of the earliest suggestions was that these were all extremely heavy neutrinos. But as we've refined measurements of the neutrino mass, we can essentially exclude these objects. They're simply not heavy enough to explain what we see. The two current leading candidates for what the dark matter is composed of are a class of particles called axions, which were originally proposed as a solution to another problem in the standard model of particle physics. And then a class of particles with masses around 100 GeV, which are loosely termed WIMPs, or weakly interacting massive particles. So most of the dark matter work that we're actually doing nowadays, both in the US and a number of international collaborations, are based upon searching for these WIMP particles. So this isn't a single particle. I should emphasize this is a class of particles. Could be more than one thing. At the moment, we don't know. So what we're trying to do at the moment is really get solid detections of these things so we can start to narrow down and classify what these objects are. There's then a whole host of more exotic candidates which, while they look good on paper, probably don't have much basis in physics, so these are largely rejected these days. So just before I start talking about WIMP detection, which is the main focus of the experiments that I work on, I'll touch very briefly on axion detection, which is the other branch of experiments that I work on. I don't have any skin in the game, I just build the experiments, I don't worry too much about the science case. Axions are a very unusual particle. They are extremely low mass, although we don't have a very good handle on what that mass is at the moment. but they have a very unusual property that through a process called Primakov conversion, they can interact with a strong magnetic field and produce a photon. So this conversion effect gives us the opportunity to build a number of very interesting experiments to actually try to detect these things. This conversion can be done in a controlled environment, such as a microwave resonance cavity, which is the basis of this experiment I'm highlighting here called ADMX, the axion dark matter experiment. But it also leads to a number of other interesting effects, such as this photon regeneration, which is gaining a lot of interest nowadays. Photon regeneration can literally be thought of as light shining through a wall. The process for this kind of experiment is essentially the reverse of this Primakov conversion effect. You have a photon coming in, interacts with a magnetic field to produce an axion. Now if we put a wall here, the photon can't go through, but the axion can, and we can reconvert it back into a photon on the other side. So they're very early days for this kind of experiment, but this potentially leads to some very, very exciting results. In the meantime, we're working with a number of these microwave cavity type experiments, such as the ADMX experiment, which is currently operational at the University of Washington. I mentioned this one in particular because there's been a big media furore in the last couple of weeks with some new results that ADMX has published. We have the proper paper here and then the popular science version on the right, just so I can get our technician's picture in. Recent results from this experiment have actually confirmed that the experiment has reached a point where the noise in the detection method is low enough that we should start to be able to see axions. This is a slow experiment because we don't have a very good handle on what the axion mass actually is. But now that we know that we have a reasonable chance of detecting it, it's just a matter of time until the experiment actually finds something. But leaving axions for the moment, and we'll come back to talking about WIMP detection. So, the inherent nature of WIMPs is such that they don't interact very well with normal matter. They do interact, but it's a very, very rare kind of event. For example, if the theories are correct, there's millions of these particles going through this room at the moment, and we're simply not aware of them. There's two major ways that we can try and detect these things. These methods are broadly classified either as indirect, where we try to see some secondary effect of the WIMP interacting with a normal matter target. The other class of experiments are imaginatively known as direct methods, where we actually try to see the WIMP particle itself. Indirect methods are typically cheaper and easier to implement. So of these four experimental examples I'm highlighting on the slide here, I won't go into these in any great detail. These three blue ones are all indirect detection methods. Now, typically, these are very easy to make very large experiments. They use very cheap materials. From an engineering standpoint, although they're not straightforward, they're certainly not a huge challenge. However, they do have the limitation that they typically are more sensitive to the higher end of the expected mass scale for WIMPs. So in this case, high mass is meaning larger than about 10 GeV particles. If you recall on the earlier slide, I pointed out that WIMPs are kind of around 10 GeV. They could be anywhere below that, could be above that range. But a lot of these indirect methods aren't very sensitive to the low end. And interestingly, as a number of these experiments are putting better and better limits on the WIMP mass, we're actually finding that the results are favoring the low end of this mass scale, so below 10 GeV. So there's now been a lot of renewed interest in this more challenging detection method, which I broadly term here as cryogenic, of which the CDMS range of experiments is one of the world-leading examples of this kind of detection. So the Cryogenic Dark Matter Search collaboration has been in existence since around the mid-1990s. It currently comprises over 100 scientists and technical staff working at 21 institutions, largely in the US, but also with a couple of partners operating in Canada and the United Kingdom. The collaboration has deployed a series of progressively more sensitive and more advanced experiments. The first generation of experiments, CDMS-1, was deployed at the Stanford Underground facility and operated from around the mid-90s to the early 2000s. At that point, the CDMS system was upgraded and relocated to a deeper underground site at the Sudan mine in Minnesota. It's a very pretty area in the summer. I highly recommend a visit, although not in winter. This version of the experiment operated until 2008, when it was upgraded with a new series of more advanced, more sensitive detectors, and became known as Super CDMS Sudan. This experiment operated for around 5 years in the mid sort of 2010s. The experiment was recently decommissioned and the equipment mothballed, largely back to Fermilab, so that we can overhaul it and install it in the latest generation of the experiment, Super CDMS SNOLAB. The expectation is that we'll be deploying this experiment within the next couple of years. We've just received construction approval from the Department of Energy and also from the National Science Foundation. So it's a small experiment on the scale of particle physics, but it's a major undertaking both for the US and the Canadian government. So the basic approach for CDMS is to place a high mass object in the way of the dark matter and wait for the dark matter to come to you. So early versions of the experiment were based around high density semiconductor materials such as silicon and germanium. A couple of examples in the pictures here are of actual Super CDMS style detectors. For a sense of scale, this is a raw germanium ball on the right here. This is around 4 inches diameter, about 1.5 inches thick. We use these high purity materials for a number of reasons. One of which is that they have a relatively large interaction cross section with the dark matter particles because of their high density and crystal structure. It's relatively easy to obtain them free of radioactive contamination. I'll talk a little bit more about this in a moment, but we are looking for very, very rare, very, very sensitive events. So environmental background, even the intrinsic radiation from basic materials and dirt will completely swap the dark matter signal. So this is a major challenge for this kind of experiment, which isn't usually seen in some of the indirect detection methods, which is why those are typically the ones people like to try and implement. The other advantage is that we can actually directly turn these crystals into our detectors. We don't need a separate detector system. We can use conventional semiconductor processing and lithographic techniques to pattern our detectors directly onto the surface of the crystal. It may not show up too well, but in this completed detector on the right, these very faint lines that you can see are actually circuitry. So we've gone from a raw crystal to our dark matter detector by direct processing of these lumps of semiconductor. So the way these detection systems work, as I mentioned, we're looking for lumps slamming into our crystal, and then we measure the effect of that interaction. Unfortunately, everything slamming into the crystal causes similar effects. So the challenge is to really pick out what is a dark matter interaction and reject everything else. So one of the first differences between these two kinds of interaction is whether the interacting particle interacts with the nuclei in the crystal or with the electrons in the atom. So the broad classification of the signals that we actually see are nuclear recoils or NR events and electron recoils or ER events. The NR events are potentially signal, although not necessarily. The ER events are definitely not signal and need to be rejected. So these nuclear recoils can arise from our WIMPs, but they can also arise from neutrons and other relatively dense radioactive particles. Alphas would have a similar kind of effect. The electron recoils are a relatively common interaction. These result from interactions with photons, electrons. Again, alpha particles tend to interact with everything because they're so big. As I mentioned, to determine whether what we're seeing is a dark matter signal, we have to be able to tell these apart. Fortunately, we do have a way to do that. So the detector style that we use for the CDMS system is what's known as a ZIP, a Z-sensitive ionization phonon-mediated detector. Again, a little bit of a mouthful, but I'll try to explain what that is. Essentially, this processed crystal allows us to measure both the ionization effects of the particle interaction, the charge effect as electrons and the particles are stripped off of the atoms in the crystal, and also the recoil energy as the nuclei themselves recoil from having this very, very large WIMP particle slamming into them. And what we find is that the ratio of the recoil and the ionization signal allows us to discriminate the electron recoil events from the nuclear recoil events. So this plot here on the right, these measurements are made with calibration sources. Essentially, you expose the detectors to a known radioactive source and look at the resulting signals. This upper cluster of signals which have a high ratio of ionization to recoil energy, these we can say are electron signals. This lower cluster with the reverse ratio are nuclear recoils. So these are potentially the ones that we're looking for. The way we measure the recoil energy is interesting. So charge is a relatively easy thing to measure. You just stick a couple of electrodes into your crystal and you can just measure the potential difference across the detector between these two sets of electrodes. To measure the recoil energy, we actually need to look for the very, very small amount of heat that's deposited in the crystal by this WIMP slamming into it. Now this is an extremely small amount of energy. Even for a massive particle like a WIMP, we're talking femtojoules. To measure this, we need probably the world's most sensitive thermometer. So borrowing techniques which actually started out in the world of astronomy for measuring non-visible photon signals, we can build what is known as a bolometer. Now a bolometer is a total power detector. I'm not going to go into a lot of details to how these things work, but little cartoon on the left here, we can absorb energy in this upper part of this sketch, and then that energy is not sucked out to the heat sink because we control the thermal conductance between the absorber and the cooling sink. And then we can measure the very small temperature rise that we see in this absorber. Now, this cartoon makes more sense if we're talking about somebody shining light on a detector, but the principle is exactly the same. There's a number of ways we can build these thermometers, but the best and most sensitive way to build them is to use what's called a transition edge sensor. Now this is a superconducting film which operates right in the transition between the normal and the superconducting states. So this inherently is at low temperature, which I'll speak to a little more in a second. Superconductors, when they're cooled below what's referred to as the critical temperature, display an interesting phenomenon when they have zero electrical resistance, which is what's shown to the left at this point. If we warm them up a bit above their transition temperature, they behave like a normal resistor, which is what we see to the right. If we sit right in the middle here, this sort of temperature change, this curve, this width is about a millikelvin, something of that sort of order, very, very narrow. Any heat deposited is going to result in a huge resistance change and shoot this bias point off over here to the right side. So this gives us still a small signal, but something that we can measure. As I mentioned, these superconductors need to be operated at very low temperature. We would have to do this anyway because the inherent thermal energy in the detector crystals themselves far outweigh any signal strength that we're going to see from the dark matter interaction. So in the case of Super CDMS, we actually operate at a few tens of millikelvin above absolute zero. So one of the challenges is to cool these very, very large crystal masses to this extremely low operating temperature. So we've built our sensitive detector, but we still have the problem that we can't tell the difference between WIMPs and normal interactions coming from neutrons. The only way we can tell these apart is to try to minimize the number of neutron interactions that we actually see. The way we deal with this is threefold. First of all, we have to be very careful about the materials that we select to build our experiment, which unfortunately excludes most of the materials that you would actually want to use to build a cryogenic experiment. Even something as simple as a piece of copper could be mildly radioactive. So we need to be very careful to account for what we're actually putting into the experiment. We need to measure absolutely everything and build a very detailed model of what's in the system so that we can know whether what we're seeing is something real or whether it's just coming from the background. The second part of this strategy is we shield the experiment. We can use a lot of very high density materials to prevent environmental neutrons and gamma particles from reaching the actual detectors. We use a combination of, say, high density materials such as lead, also high density plastics, and water is a very, very good shielding material. Also has the advantage of being relatively cheap. The final part is to try to get away from as much of the background radiation as we possibly can. And we do this by going to deep underground sites. WIMPs will quite happily pass through the Earth and out the other side. But if we have a reasonable amount of dirt between us and space, we can screen out a lot of cosmic rays, in this case, muon interactions. So, underground science is something which has been very commonly done in particle physics for a number of reasons, one of which, as I say, is to get away from this intrinsic cosmic ray radiation. The plot here that I'm showing is a plot of the relative muon flux, which is the major contributor of a major component of cosmic waves, as a function of depth. So I mentioned the Sudan site, which is where CDMS-2 and Super CDMS originally operated. That sits up here at about the 10 to the, what is that, 10 to the 5 sort of intensity. The site where we're looking to deploy the new experiment is all the way down here. So sea level exposure on this scale is kind of up here somewhere at about 10 to the 9, about 10 to the 9 interactions per year. So the Sudbury site where we're looking to deploy this experiment is around 7 orders of magnitude lower background than it would be operating the experiment at sea level, 3 orders of magnitude better than the original Super CDMS site in Sudan. So this leads us to SNOLAB. SNOLAB is currently the deepest underground laboratory site in North America. It briefly was the deepest in the world, but not at the moment, but I say it is the deepest in North America. It's located in an active mining complex in a town called Greater Sudbury in Ontario, which is around 200 miles northwest of Toronto. Very pretty town, actually. It's very nice to visit here again in summer. Wouldn't advise it in winter. The SNOLAB site is around 2 kilometers underground, and it's in a corner of an active working mine referred to as the Crichton Shaft. This is located in a geological formation called the Sudbury Basin. The basin was formed around 2 million years ago from a meteorite impact, and this is actually one of the largest nickel-producing regions in the world. There's a huge amount of really high-quality ore coming out of this mine. Operations at SNOLAB started around 2009-2010. As I mentioned, it was briefly the deepest lab site in the world, but was very quickly overtaken by the Jinping Underground Laboratory in China, which is around 400 meters deeper. However, the Chinese construction, they cheated. They drilled into the side of the mountain, so you can just drive a truck in rather than having to go underground. However, say SNOLAB is still the premier deep site in North America. This is a slightly old plot here that shows the Crichton Mine complex. These horizontal lines at the various levels where ore's been dug out. So the SNOLAB site is all the way down here at what's referred to as the 6,800 foot level. This, to say, is out of date. The active mining operations now extend down to about the 9,600 level, and they're mostly going this way. So the mining operations are getting further away from the lab, which overall is a good thing. And as I mentioned, there's a lot of nickel here. This commemorative nickel, which is about 30 feet in diameter, was erected as part of the Canadian Centennial celebrations. All of this ore was dug out of the Great Sudbury Basin. The lab was originally constructed to house the SNO experiment, the Sudbury Neutrino Observatory. This was a 6-meter diameter sphere filled with about 1,000 tons of heavy water, deuterium oxide, which again has a very, very large interaction cross-section. In this case, this was one of the first experiments that was really able to measure the solar neutrino flux. This was kind of an interesting experiment. In this artist's impression, this inner structure is the sphere containing deuterium oxide. It's surrounded by a cluster of photomultiplier tubes. This outer cavern, which you can see in this sort of fisheye lens here with operators, this cavern is completely filled with conventional water during normal operation to provide background screening for the central experiment. The SNO experiment ran very successfully from 1999 to 2006, and it's currently being overhauled as the SNO Plus experiment. However, starting towards the end of the 2010s, the SNO site was greatly expanded with a lot of new dedicated lab facilities to form the SNO lab facility. In this cartoon map we see here, these older wiggly tunnels down towards the bottom are part of the old original SNO complex. This cavern here actually is the SNO detector that we saw on the previous slide. The new construction is this nicely laid out rectilinear structure up here to the north. What this facility has done is added around 33,000 square feet of new dedicated experimental space. The whole of this lab is actually a Class 2000 clean room, which makes it a fantastic experimental space, both for particle physics, but also for a number of other experiments. So there's all sorts of things going on in here, from geology to breeding fruit flies, in low radiation environments. When I was there a couple of years ago, they actually had a fish tank as well. I'm not sure what was going on there. But of course, operating in this kind of environment is a bit of an interesting challenge, because as I mentioned, this is an active mining facility. So there is no dedicated access to this nice clean laboratory. We actually have to share the entrance to the facility, which is a very small and very low technology cage, with the active mining crews. So we ride down on this shaft early in the morning with the mining crews down to the 6,800 foot level, and then trek about 1.5 miles through the access drift, which you probably can see in this photograph is not the cleanest of environments. To those interested, I'll point you towards this great educational video referred to as A Day at SNO Lab, which is available on YouTube. I have a short clip I wanted to show you here. It's possible this is going to completely break, but if we keep fingers crossed, I'll see if that will let me run. There we go. So you get to hang around with a lot of miners, mostly who are speaking French, because they're all Quebecois. We load into the cage, and then we ride down to the 6,800 foot level. Now, I would point out that normally this run is done with no lights, because you don't want to blind the guy that's standing 6 inches in front of your face. So this rather unpleasant journey, if you could imagine doing this in total darkness, it's quick. If you've ever ridden an express elevator or in an open top plane, the experience is very similar to that. So the full descent from the surface to 6,800 feet is achieved in about 3 minutes if there's no stops. And very occasionally you do stop at other levels. I think we just whizzed by one of the higher levels in one of these clips, maybe in this next one. There you go. Yeah, there's a mining level. There's another one. And then hopefully we slow down as we reach 6,800 foot. And we come in for a nice gentle landing, just about there. Then everybody go into SNO Lab unloads, and we trek 1.5 miles through this extremely dirty mining environment. Now, one of the strangest experiences of riding the elevator down that quickly, at 6,800 feet, air pressure is about 30% higher than you would see at surface level. So there's a lot of ear popping going on in that 3-minute ride. So these are mostly older mining operations. We come through, and I'll stop that there. And as I say, if anybody's interested, that is available on YouTube, and I highly recommend taking a look at that if you have the opportunity. Yes, there we go. So once we reach snow lab at the end of our trek through this extremely dirty drift, absolutely everything that comes into the lab has to be washed off. Not only equipment, which is what we can see going on here on the left, but also people. Anything that's been in the main drift either doesn't come into the lab or it has to be hosed off. So there's certainly no shyness in the crews going in there, because even your underwear has to stay on the dirty side. This nice image here is the clean side of what's referred to as the underground dry. On the right here are the showers. The dirty side of the dry is on the other side of these shower cubicles. Everything comes off, you shower, you come in, and then you have to dress in these clean bunny suits, which is what the operators on the left are wearing. Any large components coming into the lab also have to ride down the same shaft. So it's not a very big cage. So if you're deploying a large experiment, and Super CDMS certainly falls into this category, the whole experiment has to break down into around 8-foot modules, which are then bolted together once we get underground. But once we're in the lab, it's actually a surprisingly nice environment. Snow didn't used to have this, but underground in the new facility, there's a break room. Everything's very nice and clean. The walls are coated with a material called shotcrete, which is a polyurethane-based paint. This is necessary both to contain the dust in the mine walls, but it also allows the cleaning crew to actually wash the whole facility. And they basically do this on a continual rotation to maintain the very, very high quality clean environment. One of the key improvements with Snow Lab is proper bathroom facilities. I'll leave working with Snow to your imagination on that front. So I think that's about all I wanted to talk about, and I think that was right on time, which is an unusual one. But just in summary, I hope I've convinced you that dark matter is actually a thing and that it's worthwhile to be looking at. But also that it's a challenge to look at. So we have to go to these extreme lengths to build successful experiments, but we're nearing the point where we would actually expect to get a successful detection of a dark matter particle, certainly within the next decade. If we don't see anything, there's something pretty serious with that. So thank you very much for your attention.
Just a few minutes for a general question, and then we'll let those of you who are here for extra credit depart at 5 o'clock. So let's take 1 or 2 general questions, and then we can start. So, do you have any questions first?
We're currently starting the true construction phase. We expect to be deploying over the next 2 years with a view to starting operations in 2021 with an initial run of 5 years.
How do you actually make a detection? What do you measure?
What we look to measure is the effect of the wind interacting with the semiconductor crystal. So what we would see is a little charge signal, a little change in the potential across the electrodes on the detection crystal, and also a very small thermal signal by looking at the output of those sensitive thermometers. And then hopefully we see more signals, because one isn't enough for a successful detection.
Do you have multiple sensors?
Yes. The crystals that I showed are considered a single detector element. There's a number of sensors patterned onto that. I didn't go into too much detail for the sake of brevity. But one crystal essentially is multiple sensors, because we have position sensitivity, and that's part of the background discrimination techniques. We then have multiple crystals to increase the overall interaction cross-section of the experiment. So the initial 5-year deployment I mentioned will only have a very small detection mass. We're initially deploying around 20 kilos of semiconductor. Ultimately, we hope to upgrade that to about 200 kilograms by adding the crystals.
At this point, those of you who have extra credit, if you could depart as quickly as possible.
operating at such ultra-low temperatures, we actually have to use a refrigeration technique called a dilution refrigerator. What this is essentially a heat engine, but it uses a mixture of superfluid helium-4 and helium-3. And by using a mixture of these two fluids, you can achieve these ultra-low temperatures. So 4 Kelvin is actually one of the warmer guard stages, essentially. We're actually not using much in the way of liquid helium, though. The earlier generations of the experiment did use liquid cryostats, but that involves a lot of maintenance, hand-holding, regular replenishment. So to get away from that, we're actually converting to a new class of refrigeration machines called pulse tube coolers. These have been around for a few years. They're quite frequently used in commercial electronic systems, and they're also quite popular in the military for infrared, like night vision goggles, that sort of technology. But the technology's reached the point where we can have multiple mechanical closed-cycle coolers cooling different thermal stages of the experiment, such that we don't need to pour liquid helium or liquid nitrogen into the system.
You have the next one, sir.
Yeah, are white holes a possibility for being a source of dark matter?
They would fall under the macho category, I think. So while it's not impossible, I think the evidence points towards something more exotic. That certainly could be a part of it, but it wouldn't explain everything.
And are you getting good results from these?
We have gotten very good results. As I mentioned, the earlier version of Super CDMS operating at Sudan actually holds the world-leading limit on the WIMP mass. So we had a few detections, but as I mentioned, a few detections aren't enough to start publishing papers or writing Nobel speeches. But there was that sort of tantalizing hint that maybe if we just go a little bit deeper, a little bit more sensitive, we'll actually start to see something.
Is there a point in outer space where you'd say if we haven't detected anything by this point, then all of our current models are wrong? Doesn't mean there can be another one further on. But
probably in about 5 years. The ultimate limit for this kind of detection is what's referred to as the neutrino floor. At some point, you actually become so sensitive that you're seeing direct interactions of solar neutrinos with the detector crystals. The moment we're not quite at that point, the neutrino detections that we've had so far have been in these large liquid scintillators, such as the SNO experiment. We expect to hit the neutrino floor with the Super CDMS experiment in about 5 years of operation. So if we get there and we still haven't seen anything, it's probably time to start looking for accidents.
Hunter.
Yeah, so I think you mentioned that the detector you use is actually like germanium. Is there any advantage of using germanium over silicon or other?
There are some advantages and disadvantages of the two detector crystals. We actually tend to deploy a mix of the two types of detector. Again, I didn't go into this because that would be sort of an hour-long seminar in and of itself. Silicon does have a slightly larger interaction cross-section, but it suffers more from limitations of background exclusion and also contamination of the crystal itself. So you could build an experiment entirely with silicon, but there's a number of technological problems which would have to be solved before we're actually able to do that. So by deploying a mixture of germanium and silicon detectors, we can use the germanium detectors to exclude background events in the silicon, but we can use the silicon detectors to exclude background events in the germanium. So you actually, you want to deploy a mixture of the two, and there's some complicated optimization that says I should have 100 kilograms of one and 10 of the other, depending on what sort of environment you're working in. Ultimately, though, you would want to deploy a full payload of silicon detectors, since that gives you the best sensitivity.
Okay. And did you also mention the superconductor? What particular superconductor do you use?
The detectors that we use are a mixture of aluminum and tungsten. It's a slightly complicated structure because we're actually looking for quasi-particle production as a result of the phonon energy release in the crystal. So you use the aluminum part of the structure to actually That's where the quasi-particles are produced by the phonon, but the actual sensitive element is a tungsten fin that operates as the TES bilayer. So it's a combination of those materials, some normal metal to produce the bilayer, and also to produce the charge electrodes on the material.
That's true.
Oh, I was just curious, could you say again what the name of that, the refrigeration technology that you're using instead of the helium? You said it very quickly.
Yeah, sorry, pulse tube coolers. They started to appear around the 1960s, but it's only been in the last 15 years or so that people have been able to make very high efficiency coolers. They're not very high power systems compared to some other refrigeration techniques, but they're a lot nicer than having to pour buckets of liquid helium into the experiment.
Sure.
If you could go over what you actually detect again, it might help me. What I envision, and probably wrongly, is that there's a clustering about a certain energy, and that energy is related to the...
Yeah, the energy that we see is related to the mass of the particle that caused the interaction. So when what we're actually looking for is essentially it's two detection techniques operating in parallel. When we have a particle interaction, we'll see a charge signal. So there's a change in potential difference across the detector, just a little pulse. And again, there'll be a broader pulse, which is the phonon signal. So this gives us two independent estimates of the mass of the particle. We then use both pieces of data to exclude events that we're not interested in. And by looking at multiple events in multiple crystals, that also allows us to exclude non-WIMP interactions. So having multiple crystals and multiple detectors has the advantage that a conventional interaction, for want of a better term, such as a neutron slamming into the detectors, we would expect to have multiple interactions along its path through the experiment, whereas a WIMP passing through the experiment, you would only see one signal. So it's actually impossible to determine whether it's a WIMP or a neutron on an event-by-event basis. So what we need to do is build up broad number statistics, and so that we can reliably say, yeah, these sort of single point events, those are dark matter interactions. The recoil energy that we measure is really what's related to the mass of the interacting particle. So by looking at that distribution of the recoil energies, once we've excluded things that we're fairly sure are not dark matter, that gives us either a limit or actually a proper estimate of what the mass of the WIMP is.
But the WIMP itself is not it's bouncing off.
The WIMP kind of goes through and pings off atoms in the detector, so the WIMP carries on its merry way and out the other side with some small perturbation by slamming into these high mass detectors in the way. So it's a very, very rare event because the actual detectors, we're talking about this sort of volume. So everything else going through the lab, we're just blind to it. So you're looking for the very rare interaction in this very small volume that you hope is in the way of the dark matter WIMP that's passing through the Earth.
Thank you. Given the conditions, what would be the obvious path to improve? Would just build 10 times the number of detectors to give you
Basically,
better
yes.
things?
Yeah. It's about driving up the payload, the detector mass. But the problem there is that just increasing the detector mass doesn't help you because you also have to drive the experimental background down as well. Because adding more detectors just makes you more sensitive to background radiation as well. So the plan is that Supercilium S could be upgraded with about 10 times the mass that we're currently deploying. That operation over 5, 10, 15-year time frame would also allow us to solve a lot of the problems with the cleanliness of both the detectors and the experiment. You could then build another generation of experiment with an even larger detector mass and a lower radioactive background. So you're sort of looking at sort of factor 10 improvement in sensitivity with each new generation of the experiment. So we're already talking about the possibility of building a much larger experiment called GeoDem, which would ultimately have about 1.5 tons of mostly silicon operating at about 10 millimelvin. That originally was intended to go into a facility called Mosul, which NSF were planning to build at the Homestake site, which is currently being used as part of the Dewey experiment. But that's unfortunately been killed for the moment. That would again have become the deepest lab site available in the world at about 3 kilometers. So that would have been a fantastic facility to deploy one of these ultra-high mass experiments, but it looks like that one's dead in the water. So instead, we're looking at the possibility of deploying something that looks like GeoDem to the SNOLAB facility, so in one of the larger lab spaces that would allow us to deploy more crystals.
Did you also say you had an Axion experiment that you were working on?
Yes,
And
yes.
how
So
does that differ from your equipment differ in that experiment than here?
So it's the experimental systems for detecting axions that we primarily use. Because we're looking for these Premikov type conversions, it's in some ways a lot easier to detect axions. Nothing coming from a radioactive background behaves like an axion. So you can actually run the ADNX type experiment just at the surface. You don't need to be in a clean lab or anything. The detection method there involves placing a resonant cavity, which basically just a cylinder, nothing too fancy. Placing a cavity in a strong magnetic field. So the ADNX experiment essentially just looks like a copper cylinder about that size in the bore of a 10 Tesla superconducting magnet. And we then look for these photons produced by the interaction between the axions and the magnetic fields by scanning across a particular microwave frequency range at which the resonant cavity is sensitive to because of its dimensions. You're basically looking at the absorption at a particular resonant frequency due to the conversion sucking energy out of the magnetic field. So if you could imagine having this cavity in the magnetic field and then having a tuning rod essentially that allows you to scan across a very narrow range of microwave frequencies, if you're seeing this conversion as a result of the axion sucking energy out, you're going to see a blip in the complex microwave transmission in the microwave cavity. The only downside is that because we don't have a good handle on the axial mass, there's a huge parameter space that has to be covered. You can't do that with one cavity, so there's this whole complicated sequence of different sized cavities with different tuning rods, slightly different magnetic fields, covering very narrow frequency ranges at a time, so it's a very, very long period experiment.
What's your best guess on what's the best candidate for?
I'm not that I'm hedging my bets. I think it's a mixture of the two. I don't work too much on the theory side of it, but it would surprise me if there weren't some contribution from both types of particles. There's sort of too much physics that say both of them exist to be able to exclude one or the other. So I think ultimately we'll be able to get a good handle on the WIMP mass, and it'll turn out that there's not enough WIMPs to explain what we're seeing. So probably there'll be some contribution from the axions as well as more conventional things like primordial black holes, white holes, etc.
We have to turn the classroom over to the next class in just a few minutes. This is the last talk of our semester. For those of you taking the class for credit, we'll have our final meeting this time next week, and hopefully we'll see many of you again next academic semester for the return of the series. Let's thank our speaker again.